You know, in calculus, we talked about having something that's differentiable. Having something that's differentiable once but not differentiable twice has a certain name to it. They call it a C1 function. And then something that's differentiable 2 times but not 3 times is called a C2, etc. An analytic function is something that's differentiable an infinite number of times. So basically a C infinity would be what we would call an analytic function. And the idea behind an analytic function is that it's supposed to be a nice function. But when we're talking about differentiable or analytic and things like that, we can talk about being differentiable or analytic at a specific point, or we could talk about something with differentiability. It's easy enough to talk about something that's differentiable at a point or everywhere. Talking about something that's analytic, it's better if we talk about something that's analytic at a certain point. Let's take a look at an example that we should know off the top of our heads already. For example, if we have 1 over 1 minus x, we have at 0, at I guess A they call it, we have a power series for this. And the power series, I forgot if we use K or N or whatever. We have our power series for this, and this is technically a power series around 0. Now, if we examine the graph, which we didn't do very much in our one-day crash course on power series, if we examine the graph of this, what is that one point that we should be concerned about in this particular function? When x is equal to 1, we have a little bit of an issue, right? And so when x is equal to 0, I think I'm over here at 1, and then I suppose this is going to go up. Is that right? So when we look at convergence of the power series, or I guess technically it should be down here also. Well, we don't care about that. In terms of convergence of the power series, a power series is an infinite polynomial, and polynomials are always continuous. But we make attempts at trying to use polynomials, whether it be finite or infinite polynomials, to try to mimic any graph that we're dealing with. So when a graph happens to be discontinuous and we're trying to mimic it using a polynomial, we can only go so far, right? And so what happens here is that this from 0 to this point where you have an issue where it's undefined or whatever, however we want to call it, this is going to be define your radius of convergence. Now, if we look on the other side, we see that there's no other issues of discontinuity on the other side, right? However, the fact that this is discontinuous on the other side means that we can only go as far as the same distance going in any direction that we're considering. So this is why it's called a radius. Well, I'll tell you more of a reason why it's called a radius of convergence. But this is how radius of convergence works. If you have a center point and then you have some sort of discontinuity somewhere, that discontinuity somewhere is going to take you as far in the other direction as this distance from the discontinuity. Does that make sense? I don't know if that made sense. I can't go to 2 here because it's not continuous, but more importantly, I can't go to -2 here because the discontinuity that happens on the other side is only going to bring me as far to the other side as that distance. Does that make sense? For right now, let's call it a rule. I don't know if I can explain why. Look for radius of convergence. And so if you Google radius of convergence, you might have the answer. All right, so this is kind of like how this whole idea of this radius of convergence works. Now, if we take a look at this function, we see that if we put any real number here, we don't get an issue, right? It seems to be okay. But a couple of reasons why this is not going to be okay for your radius of convergence is still going to be 1, is that one way to obtain a power series for this would be taking a look at 1 over 1 minus x, and then I would replace x with negative x squared. You see, if I put negative x squared in for x, I'm going to get the same thing, power series. So if I do that with a series over here, I would get this for the first few terms in my series, and then I can literally just put in what I substituted over here, or I can, have a -1 outside and make it look a little nicer. I guess it doesn't really matter. So let me just put negative x squared k. Hey, you can work that out if you want to change that and to make it look nicer. But in any case, if I were to look at the graph of this, anybody know what the graph of this thing looks like? Just like as a quick sketch. Okay, well, it's an even function. It's symmetric. When x is equal to 1, or when x is equal to 0, this is 1. It's not quite the bell curve, but it's kind of like a bell-shaped curve. Kind of looks like this. Okay, so you see that it looks like it's continuous everywhere. It looks like it shouldn't have a problem, but yet our radius of convergence is still going to be equal to 1. Okay. That's because when we're looking at graphs of these things, we actually need to consider the complex plane, complex numbers. So what happens here, if we take a look at 1 plus x squared and set that equal to 0, because it's a denominator and we're going to have issues when the denominator is equal to 0. If we set this equal to 0, we've dealt with this already, right? We've had problems where we had these things, and then you get x. We have issues where? What? Plus or minus I. We get issues on those values, plus or minus I. So now, if you look at not the xy plane, but the complex plane, This is different from the xy plane that we were looking at earlier. This is actually the complex plane, where you have the set of real numbers here for your axis, and then your y-axis represents your imaginary numbers, right? We had a little exercise on this, on drawing stuff on the complex plane. Then these points that are in question are these plus and minus i's. So if you think about a complex plane and this function on the complex plane, you're going to have holes here. You can't put I or negative I into this function, otherwise it's going to be undefined. And then if you look at where your point is supposed to be, this is, again, centered when A is equal to 0. That would be over here. So this is your center point, and you have holes here. You can't have these points in your graph. How far can you go from your center point to one of those holes? It's a distance of 1, right? So here's the word radius. Every single point within this circle will converge for this power series, including all these complex numbers that are within this circle, except anything outside of that will not converge anymore. So in Calc 2, they call this the radius of convergence, and it's called the radius of convergence because when you look at this from a complex plane point of view, then you're looking at distances that describe circles and radiuses, distances that are actually radius from a circle, from your center point to the closest bad point. Singularity, it's called. We can call it bad point for now until we define singularity. All right? So that's the idea behind a radius of convergence. So something like this power series is analytic around 0 because I can make a power series around 0 with a positive radius of convergence. Okay? The exponential function, the sine and the cosine functions all have infinite radius of convergences. So those are definitely analytic, not just at 0, but anywhere else that we decide to choose our center point. Okay? All right. So that's the idea behind analytic. And this idea about finding a radius this way where we're looking at complex numbers is going to be important for us also. Okay, let's I think we were doing, this is our last theorem before we did that example that took up the rest of the class time last time. And basically any other example that we choose where we have to find the recursive relationship is probably going to take that long. Well, after a while, I think we get to do things a little quicker with little shortcuts and stuff like that. So I was interested in doing another example in 6.2. And I think Alejandro was showing me some example that used an initial condition. So I think that's worth going over. So let's take a look at a problem that might have an initial condition. I won't do that one. Let's pick one from the book. All right, let's take a look at number 19 or something. where we have an initial condition Oh, by the way, maybe I should also mention that theorem. Or is that theorem? And say a few things about this particular theorem. So if x is equal to x naught is an ordinary point of the differential equation, ordinary means we're not worried about the x naught making things explode or anything like that. We can always find two linearly independent solutions in the form of power series centered around x naught, and the power series converges at least on some interval. All right, so this is a theorem that we saw last time, and it's in your book and stuff, and then we talk about this thing being defined at a particular point. So aside from trying to figure out your power series convergence, it would be a good idea to know how far this is going to go, so that we're only going to put in the points that are allowed. Okay, so use the power series method to find the initial value problem. So we're going to assume that our solution looks like this. Y is equal to ck, and then x minus x naught to the k. I guess I should have rewritten this because I have my center point, x naught, is equal to 0, and if I just do a quick scan of my differential equation, if I put 0 into any of these things, it's not going to be a 0 in the denominator or anything like that. So I think I'm pretty good with using this. So x naught is equal to 0, so my y is equal to ck x to the k. And I think most of your homework assignments are going to be just based around 0, just to simplify things, although all the theory that they discuss is around x minus x naught business. Looks like we're going to need the first and second derivatives, so we'll figure that out. And remember the shifting when you take derivatives, 1 to infinity k ck x to the k minus 1. And then the second derivative, k goes from 2 to infinity. This is k minus 1, k ck x to the k minus 2. So now you have these things set up, and then we just plug it in, right? Just plug it in. Now this is going to be a distribution of some sort, so we might as well take care of that, and then we'll, instead of having 3 terms or 3 summation signs, I'm actually going to have 4. So let me start off by writing this with 4 summation signs, and then let me see, should be able to write small here. The x times the y double prime. So this is the summation, and k goes from 2 to infinity. I have k minus 1, k ck x to the k minus 2 times the x that I'm multiplying out here. So that's the x that got multiplied in there. Okay? And then I have minus, k goes from 2 to infinity, k minus 1, k ck x to the k minus 2. And then I have a negative x times y prime. Y prime is equal to the sum. K goes from 1 to infinity. K ck x to the k minus 1 times x. So that's just k, because I'm multiplying it times x. And then I have y, which is just going from 0 to infinity of ck x to the k. And this is equal to 0. Okay, now, what I want to do is I want to match up the powers of my x's. So how should we make it look like? What? X to the k? All right, so I want to make this first one look like x to the k. So I need to add 1 to all the k's in here, right? So if I add 1, I will have k minus 1 plus 1 is k plus 1. And then I have c, k plus 1, and then x to the k. So if I add 1 inside, I have to subtract 1 from the first number in the index. So subtract 1 gives me 1. Is that good? All right, so this one I have to shift by 2. I want to add 2, or k plus 2. Replace it with k plus 2. Wait. Yeah. So add 2 to this. I'm going to get k plus 1, k plus 2, ck plus 2, and then x to the k. And then, so I shifted by 2, so this will start at 0. And then this one is already, these two are already to the k, so to infinity, ck, and x to the k. All right, so now that the k's are all matched up, the highest index is 1, starts with 1. So I got a couple of k's equal to 0s that I want to take care of over here. So I'm going to get those k's equal to 0s from these two. So let's get rid of that, or let's take care of that. K is equal to 0. What happens when k is equal to 0 here? This is 1 times 2, 1 times 2 times c2. X to the 0 is just 0, or is just 1, sorry. And this one is going to have a k is equal to 0 as well. So this is negative, yeah, thanks. And this one is a positive, and this is k is equal to 0, x to the 0. Okay? And then now, let's, I don't know if it's worth doing this, but let's put everything into one summation sign. K goes from 1 to infinity. And these all have an x to the k in them. And what else does it have? So it has a couple of CKs, and it has CK plus 2 and CK plus 2 and CK plus 1. So let's see. K plus 1, CK plus 1, minus K plus 1, K plus 2, CK plus 2. It's like I wasn't really and then these two are both CKs, so maybe I can factor out a CK and just say, I'll use this one first so I don't have a negative, so it'll be 1 minus K. Okay. All right, so let's see. Let's go to a new page for this. So we need to identify some sort of recurrence relationship between them, between these things. And, the good thing is that they're all equal to 0. So I have minus 2C2 plus C0 is equal to 0. So I have a relationship between C2 and C0. Now when K is equal to 1, I have to put 1 in here. So I got 1 times 2, C2, 3. No, K is equal to 1, right? 1, 1. So C2 first. Is this a C1, K plus 1? So C2 minus K is equal to 1. This is 2 plus 2 times 3. C3 plus, then that's 0. That's equal to 0. When K is equal to 2, I have 2 times 3, C3 minus 3 times 4, C4 plus, this is going to be negative 1. I don't seem to have a C1 here. Am I doing this right? There's no C1. All right. All right, so K is equal to 2. That looks like that. K is equal to 3. So this is 3 times 4, C4 minus, this is 3, 4 times 5, C5 minus 2, C3. 0 equal to 0, and let's do one more. K equals 4. It's 4 times 5, C5 minus 5 times 6, C6, plus negative 3, C4, 0. All right, let's see if we can get some stuff out of this. We got C1, or there is no C1, so C naught, C2 is equal to C sub 0, negative, negative, becomes a positive, becomes that. I have C2, so let's figure out what C3 is equal to. C3 is equal to 1 times 2 C2 divided by 2 times 3. The negatives cancel. So C4, wait, what's C2? Let's see if we can just simplify all this. So C naught over 2, C naught over 6. All right, so C4 is equal to C2 minus 2 times 3 C3 divided by negative 3 times 4 C4. Let's see. C3 is C naught over 6, and that would cancel with this. So that just be C naught. C2 is C naught over 2 minus C naught divided by negative 2 or negative 3 times 4. Wait. All right, so this is negative 1/2 on top. And this is 12 in the bottom, negative, so that becomes a positive 24. So C5 is equal to, what's this equal to? 2C3 minus, let's just say 12C4 divided by 20. Negative 20. And C3 is C naught over 6. C4 is C naught over 24. Okay. And negative 20. Whoa. So this is 3. This is 2. Is this like a C naught over 6 or something? So the numerator would be negative C naught over 6. And then bring that down. Negative, negative is a positive. C naught over 6 times 20, 120. Maybe we should have kept all those, because this looks like 3 factorial, 4 factorial, and 5 factorial. Let's do one more. C6 is equal to positive 3 C4 minus 4 times 5 is 20. C5 divided by negative 30, where C4 is equal to C naught over 24, and C5 is C naught over 120 divided by negative 30. So some canceling here. We get 8. We get 6. And, oh, common denominator between 8 and 6. So go ahead and add that. 24 minus 4. So C naught over 24? It'll be negative, right? So minus C naught over, what's 24 times 30? 720. Is that 6 factorial? All right. So it looks like we got a pattern for this. We have these values. If we backtrack to our first and second derivatives here, and take a look at our initial conditions. Let's put this over here. When y is equal to 0, or when x is equal to 0, y is equal to negative 2. And if you imagine your y as a series, everything except for the very first term has an x in it, right? So if I put a 0 in for x, everything except for the first term is gone. So C naught looks like it's going to equal to negative 2. So similarly, if you take a look at your derivative, y prime is equal to C1 plus 2C2x plus everything else is going to have an x in it. So when you put 0 in for x, everything is going to disappear except for C1. So C1 is equal to 6. Okay? Yeah, so I think we're good with the answer. Well, we will need it because that's part of our answer. All right. So your answer is y is equal to C naught plus C1 x plus C2 x squared plus C3 x cubed plus C4 x to the fourth plus, okay, I'll stop. And according to this, we have C1 is supposed to be equal to negative 2. Or C sub 0 is equal to negative 2. C1 is equal to 6. C2 is equal to C naught over 6, right? C naught over 2, yeah. So C naught is equal to negative 2 over 2. We'll probably simplify that. C3 is C naught over 6. C4 is C naught over 24. And so on. Can we find a pattern? We found a pattern for this, right? So C5 is equal to this, or C2, C3, C4, C5, C6 is equal to this. So Cn is equal to what? C naught over n factorial. So if we can find a pattern for this, then we can have the rest of the series figured out. So negative 2 n factorial x to the nth power. So everything except for this very first term is that weird thing that happens. Okay? Look cool? Look interesting? All right. So I suppose we can write this resembles the exponential function. So this looks like an exponential function with either some linear term taken out or added in or something like that. So if you really, really, really want to do this, you can find an actual function for this. All right, I think that's good. You guys can handle these types of problems, I hope. So remember, try to write neat, small, be meticulous. Don't lose any negative signs or accidentally change one of the 2's into a 3 or something like that. And I think the biggest deal is to shift your indices correctly so that you're matching. So after I shifted my index, I isolated these terms that came from the k's equal to 0 things, and sometimes you might have to have a couple of loose terms before you establish some sort of recurrence relationship. All right, no more questions? I feel like you have some questions, but
what is that?
you can't ask.
Because of the, like, that's like, it's just like you multiply the path by -3.
Yeah, so
That's just because of the initial value?
probably. Well, no, that's not because of the initial value. The initial value is what gets you that 6, that C naught, C1, yeah. So this is your C1.
Yeah, but is there like a reason for it not to be part of the path?
No, you can probably, like I said, you can probably think of this as -2 times, and this looks like the exponential function, right? So just e to the x, and then you subtract out some linear term. I don't know, okay, I'm running a b times x. That would change this term. It's supposed to be, what is it supposed to be? It's supposed to be -2 times, or divided by, yeah. Yeah, so if this is -3, then that would wipe out the thing. All right. So let's see if we can dig into some more theory behind these power series solutions. Oh, radius. Should we figure out the radius of convergence? No, let's figure out the radius of convergence in the next section. All right. So singular points There's we mentioned ordinary points already, so let's mention what an ordinary point is again, and go back to the problem we just did and see if we can identify that as an ordinary or singular point. So if we have a differential equation, again, we're going to stick with second order now. We're not going to restrict ourselves to constant coefficients anymore, but just it could be any function like we just did. So a point x equals x naught is an ordinary point if you divide out by a sub 2 over there, and then p and q are both analytic at x naught, or yeah, at x naught. And a point is not ordinary if the differential equation is has some issues with that thing. So let's take a look at the problem that we just did. What was it? Minus x. Let's take a look at this problem that we just did, and it's currently this form right here. If we want it to look like the second form over here, what's it called again? A normal form or something? Standard form. We can divide by 1 minus x. No, there's no prime in this one. Analytic means that you can find a power series around that point. So in this case, if we have x naught is equal to 0, if I look at my new functions p and q, if I put 0 in there, I'm not going to have an issue, right? In fact, this is your Q is actually your, what's that called again? Geometric series that was centered around 0. So in this case, 0, these functions are analytic around x naught is equal to 0. So 0 is an ordinary point. On the other hand, if you have x equals 1, then we have a problem. So x equals 1, these two functions p and q are not analytic because 1 is an issue point for these two functions. So this is not analytic. It's not an ordinary point, so it must be singular. So this is a singular point because of that function that was divided out. That function is equal to 0 when x is equal to 1. So that's a singular point. Okay? So singular points are going to be a little bit of an issue for us because we can't take power series around those singular points. And this particular problem is not a big deal because we usually like to have our ordinary points or have our x naughts around 0. So singular points. The differential in terms of the differential equation, if you wanted your differential equation around 1, we're going to have a problem. So this is a problem. This is a problem. If we tried to let our y equal to a power series that revolved around 1, where we wanted 1 to be a center point, then that's going to be an issue. So what we're going to need to do is we're going to need to change our strategy. We can still try to do it, but we're going to need to change the strategy for our power series solution. So the solution will not work. And depending on what kind of, quote, singular point this is, we might have a way to deal with it. Okay? All right. So let's take a look at a singular point and see if we can classify that even further. And this is kind of like a funny way of putting it. Could probably try to express this in a simpler way that doesn't require all these weird equations, but let's take a look at it. A singular point is said to be a regular singular point. So let's underline regular singular point. If the of a differential equation, if the function p and q are both analytic. And a singular point that is not regular is said to be an irregular singular point. Okay. What? Again, looking at the example that we were just looking at, we found that we have a singular point when x is equal to 1. So we divided out the 1 minus x. And then we identified these as your capital P. That's the other thing, is they use the same letters, except one's capitalized, one's lowercase. So far we know that x naught is equal to 1 is singular. So we know that that's a singular point. So what we need to do is we need to figure out, according to this, we're going to define a new function, little p of x, equals x minus x naught, so that's x minus 1 times p of x. This is your p of x. And then we define little q of x to equal x minus 1 quantity squared times capital Q of x. Okay? So if we simplify these two functions, we get p of x is equal to, now the numerator and the denominator and this x minus 1 cancel with an extra negative sign. So that's just x. And x is a nice polynomial function, so this is analytic. And then if we do the same thing and simplify q of x, I'll cancel with a negative sign, but I'll still have an extra x minus 1 in the numerator, which is also analytic. So the fact that these two new functions are analytic means that x equals a 1, it's a singular point. It must be a regular singular point. And if you have a regular singular point, it turns out that we can deal with this with a series. If we wanted a series around x naught, or x naught is equal to 1. Okay? So that's a definition of a regular singular point and something that's an irregular singular point. Can you give me an example of something that might be an irregular singular point? Let's see. See if I can come up with one. The ln function is usually not a good function to deal with. So that if you work this out so that you're in a normal form, we have a singular point at x is equal to 0, right? So now with that singular point, let's ask, is it a regular singular point or an irregular singular point? So if we take x minus 0 times your p of x and if we take q of x equals x squared times 1 over ln x, these two functions are not analytic. So we're not going to be able, so these are irregular. Or not these, but this point, x is equal to 0, is an irregular singular point. And what that would mean is that you're probably not going to be able to find a power series solution for irregulars. You're not going to be able to find a power series solution around 0. Now, you can probably still find a power series solution around a different point, like x is equal to 1, but it's not going to work for 0. Yeah?
And if you had one that wasn't a analytical, but the other one wasn't, it's still irregular?
It's still irregular. It has to satisfy both. Okay? Questions? All right. So how do we solve, at least for regular points? Let's take a look at regular singular points. How are we going to be able to solve for regular singular points? So Frobenius has something for us. And the thing to do with Frobenius' theorem is to multiply your power series by some multiple of x minus x naught. So if you have a regular singular point of a differential equation, then there exists at least one solution that looks like this. Now, unfortunately, r is a constant to be determined, and so you can't start off saying, okay, I want r to be this. So r is going to be something that you're going to have to determine eventually throughout your solving for this. And so you'll get this series to converge for some radius of convergence. So as if the power series problems aren't hard enough, now we're going to have to throw in an extra r in there that we're going to have to deal with. So let's we can look at a problem that we're not going to do in 4 minutes. There's some classifying. Well, I suppose we should just classify them right now, and then we need to, there's another topic that we need to discuss still to be able to continue on with our solving for this. So each of these things are supposed to have singular points, and we're supposed to classify the singular points as regular or irregular. Let's take a look at the first one. We got x cubed y double prime plus 4x squared y prime plus 3y. So what are we supposed to do? What? We're supposed to divide by x cubed y double prime plus 4x squared over x cubed y prime plus 3x cubed y. So your capital P of x is what? So little p of x is, so this is around x is equal to 0, right? So x minus 0 times capital P of x 4, and we don't have an issue with the denominator there, so this is analytic. And Q is 3 over x cubed, and little q is x squared times 3 over x cubed, which is 3 over x. So this is not analytic. So what can we say about this? It seems to be irregular. Right? So let's take a look at number 2. We have time? Well, we're out of time. Yeah?
Sorry, for these, we don't care what the point is, we just know it's irregular.
Yeah, so we just have to, well, the point at x equals 0 is irregular. So for this one, we actually have 2 points to look at. X is equal to 0 and x is equal to negative 3. So there's 2 points to look at.
That's how you find their, oh, well, yeah, you have to do, okay, yeah.
So you have, for each of those, each of these singular points, you have to work this out to see if whether it's each of them is regular or irregular. All right? All right. Good luck with your homework.